Hello class, this is CSE-5250. Is the fan loud right now? Alright, let me fix that. Okay. Hello class, this is CSE-5250, sections 2 and 60, week 4, spring 2025. Okay, so let's recap what we have been doing so far. We're trying to write a pi estimating program. It estimates the value pi by adding up terms in a summation. We are parallelizing that calculation by making a multi-threaded program, but so far we have encountered a problem, and the problem is race conditions. So a race condition only occurs if we have multiple processes, or in this case threads. Race conditions can occur with either threads or processes, but if we have more than one process trying to access the same slot in memory, we have the problem of a race condition. And it's called a race condition because they're racing one another trying to get their information into that slot of memory. But the problem with a race condition is this. Well, this is something I always like to say. In a race condition, last place wins, because if you're first to be overwritten. If you're last, whatever you have written will last. That's the value that persists. So, we have went through with writing our pi estimating program. So, now let's try to fix it up. So far, we're really dealing with rather fairly basic stuff, but really, this is stuff to know so we write code that doesn't accidentally misses any values. Because what can happen with a race condition, at least in our case, is data loss. So we're losing some terms in our summation because of a race condition that is happening in our code. So, this is going to be our next assignment, by the way. So, so this is going to be our next assignment. So, let's check out what we have in store. Okay, as I said, race conditions happen when two processes, or threads in our case, try to access a shared variable. And we need a means of keeping threads from trying to access the same thing at the same time. That is called mutual exclusion. So basically, only one thread can access this shared resource at a time. And our shared resource in our case is that shared variable that contains the sum for our summation. So the sum, that was a global variable. Every thread has access to it, and all of our threads are trying to fight one another to get access to it. This leads to a race condition. This leads to some terms being lost. This leads to our final sum being off and unpredictable also. So if you try this out, and likely you have tried this out if you've been following along with the first Pthreads assignment, when you run that program multiple times in a row with multiple threads, you're gonna get the wrong answer every time you run it. And that's unpredictable. And it's unpredictable because, well, we would need to know what the CPU scheduler is doing. What is the CPU scheduler doing? And for our purposes, this is hard to know, so we want our program to run regardless of whatever the CPU scheduler deems is ready to run on the CPU. So when we have this multi-threaded program, we have the CPU scheduler deciding which threads to run next. And again, which thread to run next, it's hard to know. Okay, so there is one way I would like for us to solve the issue of the race condition first. And I'll say right now, spoiler alert, this is an inefficient method. the reason why I want you to try this out first is, although it's simple enough, once you try it, you'll probably understand why it's so horrible. It's called a busy waiting. So, we're gonna add another shared variable to our code. It's called a flag. Well, we name it a flag. It's a flag, we name it, it's an integer value, we name flag. We're gonna initially set that to 0 in the main function. And when we set that to 0, it basically says the thread with rank 0 shall run first. Or rather, the thread with rank 0 is the next thread that can run. So when we have, let's for example say we have 2 threads. So we have thread 0 and 1, and the flag is currently set to 0. That means it's thread 0's turn to run. The idea is this: before we enter our critical section, thread 0 and thread 1 will execute this while loop here. When it does, it's gonna evaluate the expression flag does not equal my rank. So it's gonna check that expression. For thread 0, if flag was 0, flag does not equal my rank will immediately evaluate to false, and the thread will exit the loop. So while flag does not equal my rank, and then there's this semicolon here. So that is the while loop. So with this loop, it's gonna check this condition over and over and over again until it changes. With thread 0 and the flag being 0, thread 0 is gonna check that condition, evaluate that condition. It's gonna say, it's gonna determine that, okay, that's false, I'm gonna break out of the loop, and it's free to enter its critical section. Meanwhile, with thread 1, it's going to check that condition, flag does not equal my rank. Well, flag is 0 and my rank is 1. Therefore, that expression evaluated to true, and I'm gonna check that expression again. Flag does not equal to my rank. True? If true, check it again. Flag does not equal to my rank. True? Check it again, and again, and again. And thread 1 is gonna do this over and over and over again, while meanwhile, thread 0 is allowed to enter the critical section, that is, add a new term to the sum. So, thread 0 is allowed to add to the sum, meanwhile, thread 1 is stuck checking this value, this expression over and over and over again. So how do we get thread 1 to enter the critical section? When thread 0 leaves the critical section, it's going to increment the flag by 1. That way, it basically changes the value of the flag, so that value is now 1. And when thread 1 checks that expression again, flag does not equal my rank. Flag is 1. If the flag is 1 and my rank is 1, flag does not equal to my rank true? It's gonna evaluate to false, because 1 does not equal 1 is of course false. So that breaks thread 1 out of its loop, and now it's free to enter the critical section, and that is to add another term to the sum. Meanwhile, thread 0 is going to do another step. It's going to perform another iteration of the for loop, and now thread 0 is checking this expression, flag does not equal my rank. Of course it's not going to equal to my rank, because that flag is now 1, and now thread 0 is stuck in that while loop, checking that expression over and over and over again. When thread 1 exits the critical section, it's going to increment the flag again, but that would actually increment it to 2, but we do a modulus operation, so flag equals flag modulus thread count, so if we increment it to 2, it's just going to loop back to 0. A modulo operation is perform an integer division, but get the remainder instead. So if we have two threads, and we have 0, 1, 0 divided by 2, 0 divided by 2 has a remainder of 0. And then 1 divided by 2 has a remainder of 0. No, it has a remainder of 1, my bad. 0 divided by 2 has a remainder 0. 0 divided by 1 has a remainder 1. But 2 divided by 0 has a remainder 0. It's also for this reason that in the context of computer science, 0 is considered an even number. Anyway, that is the basic gist. We have a flag variable that a thread is going to check in a while loop. It's going to be blocked from entering its critical section until that flag value equals its rank. When it enters the critical section, it's going to do its thing there. In our case, increment the sum by a term. When it leaves the critical section, it's going to increment the flag by 1 and possibly do a modulo operation to make sure it moves back to 0 if needed. That allows other threads next in line to execute their critical sections. Okay? And that's just an example with 2 threads. The key thing with this is that it is scalable. So we can work with this with any number of threads we want. So be it 2 or 2000. Let me log back into my VM really quick. Okay, so previously in the last video, we got to work with writing a pi estimating program. So what I'm going to do is I'm going to make a copy of this, and it broke. Maybe I need to restart this thing. Hold on. Okay, as I was saying, last week we made a pi estimating program that has a bug in the form of a race condition. Let's try to fix it using the busy waiting. Why does it keep breaking? Hold on. Yeah, now it's rebooting. I don't know why. Right. Now, give me a minute. Okay. Now hopefully it's fine now. So, as I said, previously we made this Pthreads program here. That is our pi estimating program with Pthreads. Let's make a few copies of these, and the first one I'm gonna rename it to busy wait, and the second one I'm gonna rename to mutex. So one's gonna be using our busy wait, and the other one's gonna be using what we call a mutex. That's gonna be for a little bit later. Okay, so for our busy wait, as I said, we need to add a flag variable. Let's add it to our let's add it to our global variables up here. So int flag, and this is the flag for our busy wait. Now, in the main function, I'm going to initialize our flag to 0. So flag equals 0. Right, we're almost done. In the thread function, that is the function that every thread is gonna run. First, we need to identify our critical section. So a critical section is any portion of the code that would be accessed by more than one thread. More specifically, it would be any portion of our code that would be modified by more than one thread. And it is this line right here. This line is our critical section because we're adding a term to our global sum. So before we enter our critical section, and after we enter our critical section and after we leave our critical section, those are the lines of code that we're going to add on to. So the first one is going to be our busy wait. So we're going to say while flag does not equal my rank. And that's it. So this is our critical section, so I'll identify it as such. And now, wait here if another thread is accessing the critical section. So after we leave the critical section, we increment our flag. So we can simply say flag plus plus, and then flag equals flag modulo thread count. So if multiple threads are reading a value, that's okay, but if multiple threads are trying to write to the same value, that's problematic. So also we can simplify this into one line. Well, you can do this if you want to, and this code is legal. It's just maybe it's a little bit easier to understand if we have this separated as two lines of code where we do an increment operation followed by that modulo operation. So both ways will do the same thing. It's just one's more terse than the other, but maybe a little more too dense. Anyway, that is our program right there. Let's try it out. Okay, so now we have this program all written up. Let's right-click here, right-click in this empty space, open in terminal, and hope it doesn't crash. Perfect. So now we have busywait.c and mutex.c. We're not going to touch the mutex just yet. The command for compiling this program is the same as before. gcc-g-wall-o, the name of the executable that you want your executable to have, the name of your source code file, and then -lp thread. Since our program is called busywait.c, let's put in busywait.c here, and busywait as the name of our executable. Let me just expand this so we have a good view of the whole command. There we go. Enter. And it compiled just fine. So now if I do /busywait, I get a segfault because I did not type any command line arguments that go with it. So remember, the program is set up so the first argument is the number of threads to run. The second argument is the number of terms to add. So let's do something simple and do 1 thread and 1,000 terms. Okay, so you now have an estimated value of pi. If I run this multiple times, it's going to have the same answer every time. And that's because there's only 1 thread. There's nothing else to fight with. So therefore, it's going to produce the same answer every time. We only get race conditions if we have at least 1 more thread trying to access the same shared variable. Okay, so it's working with 1 thread, which is good. Let's do it with 2 threads. Okay, so it also works. Okay, so here's where it starts to get weird. So it worked a few times, but now the program is stuck. Let's see something. Ubuntu is really its own. Ubuntu is basically a entire computer. It is really an entire operating system. And let's see our CPU utilization. So one of them is very high, and I think we can see what's going on too. I think we can see the individual threads executing their busywaits. So 1 thread is so maybe if we really want to overload our computer. Okay, so it did work a few times, but the problem is it started to hang. What I'm trying to do is I want to see if I can see it hang. So I'm going to do busywait to 1,000. Oh, you see that spike there? That's the thread that is performing a busywait. So it's doing that it's stuck in that while loop, checking that condition flag does not equal my rank over and over again while it's waiting. So that's the problem with the busy wait. It's doing work, but it's not doing productive work. In that case, you want to do Control-C to kill the process. And now our CPU utilization will just go back down, and there we go. Nice and calm again. Let's do 10 terms and hope that doesn't crash things. Okay. That was okay. But let's do 4 terms, and I want to do 20. Let's do 4 threads and 20 terms because 4 divides 20 without remainder, but it cannot divide 10 without remainder. So let's try this. Okay, it worked again. So let's add a few more terms. 4 threads, 200 terms. It also worked just fine. Let's do 1,000 terms. It also works just fine. So, if I try it again, you see it? Now we have 3 threads doing a busy wait. Yeah. And some of the threads are flip-flopping because that is either a thread getting its turn on the CPU, or maybe the thread scheduler is deciding, okay, let's run some other thread instead. But you see the problem here? With 4 threads, we can allocate 1 to each CPU core, but with 3 of them stuck in a busy wait, they are hogging up CPU usage all the way to the max, and now it looks like we're doing a lot of work, but really we're just doing unproductive work each time. So this is the problem of a busy wait. In short, it just slows down our program by a lot. So I'm gonna leave this running and see whether it improves, but let's keep talking about what the frick just happened here. Oh no, oh no. Right. Okay, hopefully that didn't break anything too bad, but let's try that again. Yeah, so continue slideshow from current slide, and don't click duplicate, swap presenter view and slideshow. There we go. So the issue is, as I mentioned, we have a CPU that's waiting for its turn on this. We have a thread that's waiting for its turn to enter its critical section, but it's doing unproductive work. It's checking a variable over and over and over again for like it might be every clock cycle. But anyway, it's doing this operation over and over and over again. This makes the CPU look like it's doing insane amounts of work, but it really isn't. Give me a minute. Okay, so in short, the while loop that we added, that is a busy wait. The CPU repeatedly tests a condition, it tests a variable until it changes. When a thread enters the critical section, it adds its value to the sum, then increments the flag to indicate it's time for the next thread to run. But each waiting thread is doing a busy wait. And as I said, we're checking this variable or repeatedly checking this variable over and over and over again until it changes. Once again, that's unproductive work. With our pi estimating program, you have seen that it was working just fine a few times, and then it entered this state where it looked like it froze, basically. The program runs fine with just one thread because there are no other threads to compete with. But once we get to even just 2 threads, it starts to slow down. And the more threads we add, the more intolerable the slowdown becomes. And at that point, you would want to press Ctrl-C to stop your program. So we can use a busy waiting. The thing is, we can use busy waits in some contexts, but not this one. So basically, we need a different solution. So you can try this out, and you will need to try this out for your next assignment, but it's not a good solution. Here's another thing. We can actually time how long our programs run. When you run your program, before you type in the dot slash, right? Time, and then a space before the dot slash. You get the runtime from start to finish for your program. So in our case, a busy wait ain't gonna cut it. Let's do something else. We're gonna use what's called a mutex. So it's short for mutual exclusion. A mutex is a special variable that we can use with other functions to restrict access to a critical section, with the idea that we can get only one thread at a time to execute code in that critical section. Before we can use a mutex, it's also called a lock. You might, in the discussion of mutexes, you might also hear them be called locks. So we have a data type for our mutex, that is pthread mutex t. To initialize a mutex, you need to call pthread mutex init. You pass in the address of the mutex for the first argument. The second argument, don't worry about that, we'll just pass in null. Once we're done with a mutex, we need to destroy it. Once we're done with the mutex, we need to destroy it. We'll do that at the end of the program. So at the beginning of the program, we need to initialize our mutex. At the end of the program, we need to destroy our mutex because we're done with that at that point. We're going to use pthread mutex destroy for that. So we just pass in the address of the mutex at that point. Now here are the 2 functions that make the mutex basically work like a lock. They are called pthread mutex lock and pthread mutex unlock. So in the language of mutexes, this is called acquiring a lock and then releasing the lock. Or more simply, lock and unlock. So before we enter our critical section, we call pthread mutex lock and we just pass in the lock itself. Once we are done with the critical section, after we leave, we call pthread mutex unlock. That unlocks the lock, and the lock is available for another thread to use. As I said, oftentimes the discussion of mutexes has them being used as locks. As I said, we say a thread acquires a lock before entering the critical section, locking out other threads from executing their critical sections. Once that thread exits its critical section, we say the thread releases or unlocks the lock. That signals to other threads that they can enter their critical sections. Who goes next? Well, whoever is able to get the lock next, basically. With a busy waiting. One thing you might notice about the busy wait is the fact that that flag variable increments by 1 and then loops back to 0. So it is cyclical in that we have one thread and then another going up by rank and then looping back to 0. So it's cyclical. With the busy waiting, we know the order in which threads are going to execute their critical section. It's cyclical. We know what it will be. We can predict it. With the mutex, the order in which threads execute their code may change each time a program runs. This can make it more or less random, but more to the point. The randomness comes from the CPU scheduler, which decides which thread to run next. So it's not guaranteed that the order in which threads run will be in order of the rank. So it's not guaranteed that it'll be rank 0, then 1, then 2, and then 3. But for our purposes, this is a non-issue because we're doing addition operations, and addition is cumulative. The point is, every thread will eventually acquire the lock, and every thread will have access to the critical section. So, let's change our program. Let's see how our busy-wait program is doing right now. So we have 3 threads at maximum CPU utilization. Okay, so my bad. I kind of misspoke. So with 4 threads, each thread will, in theory, be allocated to one of our 4 CPUs because my virtual machine has 4 CPUs allocated to it. Oh, where are those coming from? They are coming from my host CPU, and I might be able to see the utilization from here. So 4 of these CPUs are actually these 4 CPUs because I am sharing some of my computer's resources to run this machine. So of course, 4 of the CPUs here are gonna be bogged down with work because they're actually these 4 CPUs here. Well, technically it's 3 because one of them won't have as much work. But still, that is a lot of work. The other thing is that thread scheduler might be changing which process gets to run on each thread because there are way more than 4 processes, or I guess threads, running on this VM right now. There are dozens of background processes, and they each need to turn on the CPU. So those dips might be other background processes getting a turn on the CPU. Anyway, we're probably getting tired of this program waiting. We're probably getting tired of waiting for this program to finish, so I'm just gonna Control-C and stop the whole thing. And then we should see the little line graphs dip down and, yeah, settle down. Whew, finally. Give the computer a break. Okay. Okay, let's try out that mutex. Okay, so much like the busy wait, we're gonna add a few things. First, we need a variable for our, so much like our mutex, we need another variable for our busy wait, and then we need to set that variable, and then we're gonna need to add something before and after the critical section. Oh, but we also have to destroy the mutex after that. So let's try it out. Let's create a mutex. Well, this doesn't create a mutex, it just creates a variable for our mutex. So pthread mutex t mutex. Alright, there it is. Now we need to initialize it by saying pthread mutex t. No, pthread mutex init. Pass in the address of the mutex and null. There we go. So that's at the beginning of the program. At the end of the program, let's put it after the allocate memory line. So we're gonna say pthread mutex destroy. We're gonna pass in the address of that mutex, so ampersand mutex, there we go. In our thread function, this is our critical section, same as before. Try to acquire the lock, but if it's already locked, wait for it to be available again. So pthread mutex lock. We pass in the address of the lock, of our lock. So ampersand mutex and then release the lock, pthread mutex unlock. I'll just cheat a little and just copy paste that line of code there and replace the lock with unlock. There we go. So now let's try compiling this program again. So clear. There we go. So we're gonna use the same command as we did with the busywait to compile the program, but now instead of busywait.c, it's mutex.c, and we want the executable to be named mutex. Press enter to compile. Okay, we got an error here. It's basically saying, hey, you may have misspelled this function here. So let me go back and fix that. That was the pthread mutex init. There we go. Pthread mutex init. Try again. There we go. Now let's run that program. So if I type in /mutex by itself, I get a segfault because I didn't put in those command line arguments. So let's do that with 2 threads and 100 terms. If I do this repeatedly, I'll get the same answer every single time. That means our race condition is gone. Now we're getting the same result, as we should. Let's do 10 threads and an absurdly high number of terms. Let's say 100,000 terms. It calculated pretty fast, too. So that's actually good to know. Let's try it again with even more terms. So I think that's 10 million terms, and yeah, barely broke a sweat. Let's do even more terms. I think that's 100 million, and I think, yeah, that, now so our 10 threads are each taking a turn on the CPU. There are only 4 CPU cores, so it can only run 4 threads at a time maximum. But even then, it finished up just fine. It works. Oh, now the resource monitor is trying to catch up. Okay, good. It's working. We probably want a good idea of how much faster the program is running the more threads we add. So, clear, and let's do 1 thread, and I think that's 10 million terms. No, my bad, that's 100 million terms. So 1 thread adding 100 million terms. Yeah, it was a bit slow, but it did work. Oh, my bad. I need to add the time command to that, so time mutex 1 thread 100 million terms. We try it out, and it ran at about 2 seconds. Let's do it again with 2 threads. That took about 7 seconds to run. So no speed up just yet. Let's do it again with 4 threads. And do we get a speed up again? Okay, 5 seconds. So we did get a small speed up, but it's hard to say whether that's the CPU scheduler affecting runtime. So it's hard to say. So don't be dismayed if you don't get a speed up right away. That means there's probably a few optimizations that we need to do to our program. So here's one. Here's one optimization we can do, and it is this. We are accessing the critical section every time we calculate a new term. what we can do instead is, instead of accessing the global variable sum every for loop iteration, we do that once after we've done all of our for loop iterations. So here's the optimization I want to demonstrate. We're going to add a double here, and that is my sum set it to 0. So it's going to calculate its own local sum. So we actually don't need these lines of code anymore. So I'm going to copy that and paste them out here, because it's only out here that we're going to access the, it's after we've done our for loop that we're going to access the global sum. When we do, we're not going to increment it by factor divided by 2 times I plus 1. We're going to say sum plus equals my sum. Okay, and in here, we actually don't need this or this anymore. And instead of sum plus equals factor divided by 2 times I plus 1, we're going to say my sum plus equals factor divided by 2 times I plus 1. So this should reduce the amount of accesses each thread is going to need to that global sum. Basically, we're explaining the fact that addition is commutative and associative. So if we think of our summation as being like this, it's not a finite sum because we're doing it's not an infinite sum because we're cutting it off at some point, therefore it's a finite sum. We are basically breaking up this summation into rows and then assigning each row to each thread. Because addition is commutative and associative, it doesn't matter the order in which we add terms or how they're grouped together. So even if we did this, we're still gonna get the same result as long as we add all these smaller sums. As long as we add all of these smaller sums. So each thread gets one of these sums. As long as we calculate the smaller sums and then add them to the global result, we're gonna get our estimated value for pi. Okay? Let's try it out. So once again, we're gonna try it like this, and I'm gonna save the program, and then I'm just gonna recompile our previous program. So clear. So to recompile it, that is that GCC command, gcc-g-wall-o mutex-mutex.c-lp thread. Enter. And now let's run our program with one thread. We got a runtime of about a quarter second. If we do it with 2 threads, we get a speed up in our program's runtime. So 276, that's milliseconds by the way, 276 milliseconds with one thread and 139 milliseconds with 2 threads. So we do the math really quick. 276 divided by 2 is 138. So we did get a little bit of a speed up. Yeah, see? We did get a speed up after all. So it means, in theory, with 4 threads, we should be able to cut this original runtime of 276 milliseconds into 1/4 of that time. Or at least that's the theory. Oops. 115 milliseconds. So not quite, but it is still faster than if we had 2 threads. So we should get 69 milliseconds at that point, but we got 115. That's probably because of Amdahl's law. So there are non-parallel sections of code and parallel sections of code. If we assume that our original runtime has some percentage of parallel execution time and non-parallel execution time, even if we divide that block of parallel execution time between multiple threads, we can reduce that parallel block of time to as small as we can, but there's always going to be a non-parallel block of code that cannot be sped up. So the only thing we can speed up is the part of the runtime that can be run in parallel. So we are getting a speed up after all. Neat. Okay, so there is one other thing that I would like to talk about. I'm gonna do that in the next part, okay? So I will have to stitch this video together, so yeah. Alright, so that last fix we need to do is to address the fact that our code works for whenever we have the number of terms perfectly divisible by the number of threads. So to demonstrate that, let's do this. I'm gonna run the program with, say, I'll run the program with 2 threads and 1,000 terms, and we got the answer of 3.140593. If I do the same thing but with 3 terms, I get a slightly different answer. And here's what's going on here. Okay, so let me just find it right now. So I said that the constraint is we must have the number of threads be perfectly divide the number of terms. And if that isn't the case, we get a situation where, okay, so in this example, let's say we have 37 terms and 6 threads. So 1, 2, 3, 4, 5, 6, and oops! We have 6 threads, each adding 6 terms, but we have a 37th term that's missing. So how is it going missing? Let's go back to our code and we'll add a little extra code here that says the following. Let's put it here and say percent thread %LD is adding %LLD terms %LLD to %LLD n, comma, and I'll continue this line of code on the next line. I forgot a quotation mark. There we go. Okay, so we're missing a few, so I need to pass in a few arguments here. So the first one is my rank, my last I minus my first I, my first I, my last I. There we go. Now let's recompile this program and see what's going on. So it's this long command here, so gcc-g-l and so on. Let's recompile that program and run the program once again with 2 threads and 1,000 terms. Okay, so it is adding 2 threads are adding 500 terms, 0 to 500, and then 500 to 1,000. If I did the same thing but with 3 threads and 1,000 terms, oops, my bad. So here's what's going on. So one thread is adding terms 0 to 333. The second thread is adding terms 333 to 666. And then the third thread is adding terms 666 to 999. Where's the 1,000th term? Well, it got missing. So that's what's going on, and we have to fix that issue. So we have another situation where terms are going missing. Let's fix it really quick. So actually talk about 2 ways of fixing this issue, and let's go with the easier of the 2. Solution 1 is to add a little extra bit of code. If the last thread, if this is the last thread. Have my last I be n instead. So we have threads 0, 1, and 2. Adding terms 0 to 333, 333 to 666, and then 666 to 999. That last thread should actually go from 0 to 1000 instead. So there was a missing term. And we can fix it really quick by saying if my rank plus 1 equals thread count, my last I equals n. So that's one solution. And this will work. The other solution is to have, I like to call it leapfrogging, but the more formal term is a stride. So for I equals my rank, I is less than n, I plus equals thread count. So if we have that instead, so thread 0 would be adding 333 terms, or maybe it's, actually no. Thread 0 would start at term 0, go up 3 and add term 3, go up 3 and then add term 6. Thread 1 would start at term 1, go up 3 to add term 4, go up 3 to add term 7. And then thread 2 would start at 2, go up 3 to add term 5, go up 3 to add term 5, go up 3 to add term 8. So they're kind of like, they are leapfrogging over one another so that together they add up every term, but at the same time, they don't accidentally add a term they're not supposed to, and neither do they forget to add any missing terms. Let's go with the first solution because that's the easier of the two to implement, because it doesn't require us to rewrite all that much code. But either one will work. Pick one and try it out. Let's go with the first one. So the first solution is to add that extra line of code, and that is to change my last I to be that. So if my rank plus 1 equals thread count, my last I equals n. And we can just do this to make it neat. There we go. And again, this is to make sure we get every last term in our summation. There we go. So if we compile this now and rerun the program with this many terms, now we get 3.14140,593. So thread 0 is adding terms 0 to 333, thread 1 is adding terms 333 to 666, and thread 2 is adding terms 666 to 1000. Oh, by the way, it's 0 inclusive, 333 exclusive, so it's actually adding terms up to and including 332. Thread 1 starts at 333 and stops before. Okay, so thread 0 starts at term 0 and stops right before term 333. Thread 1 starts at term 333 and stops right before term 666. Thread 2 starts at term 666 and stops right before term 1000 because it actually stops at 999. Okay, so that's what's going on here. So now we can double check our code. Let's try it with 2 threads, and there we go. We got the same answer, 3.140,593. And we can do it with, say, 7 threads, and we still got 3.140,593. And that's because we have that little check at the end that makes sure that when we divide this, when we divvy up these terms among our threads, we get every last term added to each, added in our sum. So it's the last thread that's getting all the extra terms. One other concept is called load balancing. It means one term is adding more. It means one thread is adding more terms than the others, but at this scale, this is okay. So now we fix the issue of having but requiring that our thread count perfectly divides the number of terms we're adding. Alright? We did it! We've done it. Now we have a fully functional Pthreads program that is not only multi-threaded, but also has a speedup. How neat is that? Okay, so that's going to be it on this video. So your homework is as follows. Okay, so this is assignment 2. So this follows assignment 0 and 1. So the first one is we're going to try out the busy wait. Try the program with a busy wait. Run it with 1 thread and 1,000 terms, and then try it again with, say, 2 threads and 1,000 terms. And then try to run it with increasing thread counts until you reach a point where the waiting time becomes so intolerable that you have to press Ctrl+C. Thread 1 is to try it with a mutex lock. Okay, so part 1 is to try it with a busy wait. Part 2 is to try it with a mutex lock. Part 3 is to add the code where instead of having the critical section be inside the for loop, we have the critical section after the for loop. That's how we get our speed up. Part 4 is to change the code so that we don't lose any terms. Okay? And so your deliverables are as follows. So 5 points for each thing. Source code and screenshot. Source code and 2 different screenshots. Source code and screenshot, and then source code and screenshot. Pretty simple, alright? Okay. Alright, so that should be everything for your second assignment. I will be posting this momentarily after I record it, so just keep an eye out on Canvas for any updates, okay? Alright, that's gonna be the end of the video, and I think next week we are gonna have to start talking about your project, okay? So we're gonna try to run this multi-threaded Pthreads program and see if we can observe any appreciable speed up, okay? Alright, take care, and see you next video. Bye.